Continuing on with our relative motion analysis problems, we have another system. So I have a follower hanging down from the ceiling. Here's a coupler. And here I have a disc that's basically the crank. So rather than just having a line from down here, I have a disc. And so a motor would be connected to that, and that is producing angular velocity and angular acceleration, which we have up here. 5 radians per second and 6 radians per second squared, respectively. The radius of this disc is 1/2 of a foot. From A to B is 2 feet, and from B up to the ceiling is 1.5 foot, or up to the pin. It'll be a little farther to the ceiling. O to A is straight down. So this and that are parallel, and this is at 30 degrees, A to B. Okay, and the whole problem is the goal is to find alpha angular acceleration of CB, and I didn't write the C down, so we'll put that in there. Now, notice I didn't ask for omega CB. Well, I didn't need to. There's no way you can get to this without first determining that. Okay? So you're being asked for everything. So in doing this problem, we use the same approach in all of these problems. Start from the things you know or you can use and go to what you'd like to figure out. So we know O is doing nothing. This is just the center of rotation. So knowing alpha, omega and alpha here for this link, we can figure out the velocity and acceleration of A directly. So we'll start going after that. So let's just, velocity at A, this is rotating, it's straight down, so as this rotates, we know velocity of A should be along the X. I'm not going to bother mentioning velocity at O, it's obviously 0, we can drop that from this point on. So we have omega of the disk, which we'll assume is in the Z. Cross, minus 1/2 y to get down. That's 5z cross, that's an x with a circle around it, minus 1/2 y. We get 2.5x feet per second. We can compute the acceleration of A at the same time. Again, we'll ignore the acceleration of O because it's 0, it's boring. So it's alpha of the disk cross r from O to A minus omega squared r from O to A. We know all of that information, we'll just stick it in. Alpha was 6, 1/2 down, minus omega was 5 squared, and then 1/2 down again. Do the cross products, we get 3x plus 12.5 y feet per second squared. So that's all very easy information. So now we're going to go from this point to that point. Now, I will note something. From just the geometry, it should be obvious that VB will be along X. So if I look, this is hanging straight down. As this turns this way, that's going to push that in this direction. So velocity of B is obviously going to be in the X. So note this. If A is in the X and B is in the X, VB's got to be the exact same. If you have two discrete points, if one is going in one direction and B is going in the same direction, it can't have a different magnitude. It's impossible, because otherwise it's not a rigid body. It'll be stretching or compressing or whatnot. So we have rigid bodies, so given that this is going 2.5x and knowing that this is going in the x, it is immediately obvious to us that VB is also 2.5 in the x. Also, if this has the same velocity as that does, it's then obvious to us that omega AB isn't rotating. This whole thing is just sliding at this instant across. So omega AB is 0. So that, I would argue that's obvious, but for the first time we do this, we can actually prove it to ourselves. So here we have the proof. VB equals VA plus omega cross R. So VA is 2.5 in the x. There's no y component. So when we do omega cross r, notice z cross x gives a y. The only way this can work is if omega AB is 0, because we can't get a y component. So, and once we wipe this out, if omega is 0, because the way we go from A to B is via omega cross r. So if omega is 0, it means VB, that wipes this out, so VB equals VA. So what was obvious is mathematically proven. So as a result, we know exactly what VB is. It's 2.5x as well. So knowing this is 2.5x, dividing by r right here gives us the angular velocity, omega CB or omega BC. It's all the same difference. So VB divided by r gives us 1.667 radians per second. We can put that, and this is obviously going counterclockwise. Bam, we have it in vector form. All right, so now we can go and do the acceleration at b, which will allow us to get this alpha CB term figured out. Okay, I'm going to have to move this up a bit. How far can we go? We'll bring it up to here. So we have acceleration at b is acceleration at a plus b relative to a. So here we have the acceleration of a, and then the relative part is always the same, alpha cross r minus omega squared r. All right. Notice here the omega squared, omega AB is 0, so this term disappears. So here's the acceleration of A plus alpha AB, which we'll assume is counterclockwise, counterclockwise positive, and we'll let the signs correct us. Cross, now we just have length of 2, cosine 30 in the x, sine 30 in the y. All right? Now, we can't solve this problem because we need something on the other side to equate this all to. Here's our unknown, so we can't knock this off. So we need to approach b from what's up above. So we're going to have a second equation going from c to b. So let's set that. And that's what's right here. Obviously, the acceleration at c is 0, so to go from c to b, we have alpha cross r minus omega squared r. The omega, we figured out. The alpha cb, that's the unknown. So plugging in all the numbers of everything we have, r c to b is obviously minus 1.5y, so that's a really easy thing. And so now we simply equate the x's and the y's, and we can get alpha AB, it's minus 4.81 radians per second squared. And we see that this link up here is actually angular acceleration. It's positive, so we got 5.21 radians per second squared. And that knocks off this problem. We're going to do one more, and then we will be moving on to Coriolis. And here was the answers. Give you a moment to take note of that. And we'll see you next time.